All right, hey ladies and gentlemen, here's Mr. Bryant's first video lesson for you all to enjoy. I'm going to be starting off with conservation of momentum and then talking about inelastic collisions. So hopefully all of you at some point have played the game of billiards or pool, as it's more commonly known. The goal of the game, obviously, is to strike the cue ball and to make all the other balls go into the pockets in the pool table as a result of a series of collisions. When a cue ball is traveling across a pool table, it has momentum. Remember, we've defined momentum as a product of mass and velocity. When that cue ball strikes another ball, it gives away some of the momentum it had to its target, and that other object now, that other ball, now has its own momentum. In the ideal world that we're going to be dealing with, the momentum possessed by the cue ball and its target combined is the same before and after a collision occurs. This is like the conservation of energy that we talked about in the previous unit, where energy cannot be created or destroyed. In any interaction, at least any interaction we're going to be dealing with, momentum is going to be the same in our system, the total amount of momentum specifically. The principle behind this in physics is called the law of conservation of momentum. Just like the idea that we couldn't lose any energy was the law of conservation of energy. We're going to assume again that our collisions occur in an ideal world with no friction or other forces that will cause us to lose any of the energy and any of the momentum that our objects have in a collision. In the real world, of course, these forces are important and take away some of the energy these objects have, which is why after a cue ball collides with its target, the cue ball and its target do not move around indefinitely. The type of formulas we're going to be using involve situations with different types of collisions. A collision is a type of interaction where two masses are going to strike each other physically and have a transfer of force. The two types of collisions we're going to talk about are inelastic and elastic collisions. So to give a little bit of background to this and to tie this into something that actually dramatically affected the history of our planet, not so long ago, a graduate student from the University of Arizona found evidence for a certain catastrophic event that occurred in the Caribbean about 65 million years ago. So look at all of the choices there on the screen and think about which one is the most logical or makes the most sense. Of course, there are several ridiculous Mr. Bryan answers there as well. Give you a moment to think about it before I move on to the correct answer. Of course, the correct answer is a meteor strike. There is a strike along the Yucatan Peninsula, which is on the southeastern side of Mexico. The crater formed is now known as the Chicxulub crater. Its discovery came about because researchers who were in the area found instances of compacted quartz and other minerals that were formed in the presence of extreme heat and pressure in this area. The general theory is that all of the energy imparted by the meteor when it struck the Earth not only caused massive tsunamis, but also threw tremendous amounts of dust into the air, changing the Earth's climate and making it significantly colder. Cold-blooded species like dinosaurs did not do so well in this environment, but things that could regulate their own body temperature, like mammals, thrived and became the dominant species on Earth, as it was destined to be, because humans are awesome. A meteor strike is an example of something called an inelastic collision. An inelastic collision means that one object strikes another, but they become one object and move away together. So when a big meteor comes along and strikes the Earth, the meteor and the Earth now become a single object, moving with a common velocity. A meteor strike is pretty much perfectly inelastic. It means a meteor comes in, strikes the Earth, and really doesn't bounce anywhere. It immediately sticks into the Earth and now becomes part of the Earth. The formula for an inelastic collision that relates the momentums of the objects both before and after the collision is seen there on the screen. The mass of one object times its initial velocity plus the mass of a second object times its initial velocity equals the sum of the masses of the objects times their final velocity. Notice there is only one final velocity. The reason being, of course, is after an inelastic collision, there's only one object that we're considering. Here is an example of a type of inelastic collision. We have two spheres on a string, M1 and M2. M1 is moving to the right. When it collides with M2, they move together as one mass to the right with a common velocity, Vf. Here now, we have a couple of problems involving inelastic collisions. What I would like you to do, and this is going to be part of your homework assignment for tonight, I would like you to solve these two problems. In the first problem, I would like you to solve for the final velocity with which the cat and rabbit will move away after they have an inelastic collision. In the second problem, I would like you to figure out the mass of the unknown vehicle involved in the head-on collision. It doesn't really matter whether you make this unknown vehicle mass 1 or mass 2. Remember, with this problem, you can only add like terms together. So whatever symbol you give for the mass of the unknown car can only be added to other quantities that also have that variable. Solve these questions, and when you're ready, go ahead and progress to the rest of the presentation where I'll give you the answers. For the first problem, I made the rabbit object 1 and the cat object 2. So then, I summed their two momentums before the collision, and I set that equal to the product of their masses and the final velocity. So the sum of the initial momentums of the objects is 128 kilogram meter seconds. Their combined mass is 11.5. And then to get their final velocity, I divided 128 by 11.5. Give me a final velocity of 11.1 meter per second. Notice that this value is greater than the velocity of the rabbit, but less than that of the cat. This shouldn't be surprising, considering the collision between the two objects should cause them to travel at a velocity somewhere between both objects before the collision. For the second problem, I decided to make the mass of the unknown object M2. M2 therefore appears on both the left and right-hand side of the equations. On the left-hand side, it appears as part of the initial momentum of object 2. On the right-hand side, it appears as part of the total mass of the two objects. Again, with inelastic collisions, the two masses become one mass and move away together. After I enter these numbers into the equation, on the right-hand side, I distribute the -2 into the parentheses. I then further try to isolate variables associated with M2 on the fourth line by adding positive 3,000 to both sides. In the last few steps, I add positive 7.5 M2 to both sides, and then divide both sides by 5.5 to isolate the variable M2. This means that the second car has a mass of 3,000 kilograms.